and I'm excited to talk to you about energy. So before I get started, just a brief overview of what I'm going to talk about. The main points here are doing a brief overview of where emissions are today and where they come from. Then going to decarbonizing electricity, and I'll talk a little bit about a lot of solutions that are being deployed or proposed for that. Then heating and materials, then transportation. And then I'll go into 3 topics that I think are really important. We don't have a lot of time to talk about them, which are carbon removal and carbon markets, then other greenhouse gases, which I think are something that is under-talked about and underappreciated. And then critical minerals, which is something you'll probably hear a lot when you're talking about the energy transition. So first, some context setting. So what is the context that we're talking about and where do emissions come from? If you look at, this is a chart from the IPCC. If you look at where emissions come from, the biggest part is this blue bar here, which is CO2 emissions from fossil fuel combustion, as you would expect. But there are some very important sources that are CO2 from land use change. This is basically deforestation. Then there's methane, and I'll talk a little bit about that. This is methane looking at 100 years CO2 equivalent. So I'll touch on what that actually means. And then there's nitrous oxide and fluorinated gases as well. So again, this is the total emissions. You can see it's about 59 gigatons per year. So it's really important to get some idea of what we're talking about when we talk about the energy transition and have an idea of scale so that you can say, okay, somebody's talking about kilotons. Should I care about this? Probably not. Or not that much, right? Now, if you look at just the US, and this is just the US, just for energy, so where do emissions from energy come from? This is by source. So you can see biggest one is petroleum, then there's natural gas, and then coal. And where does this energy actually go, right? For petroleum, most of it goes into transportation, as you would expect. In general, petroleum is too expensive for other uses. Then there's natural gas, which is very broken down between industry, heating, and electricity. And then coal that basically only goes into electricity. So all of these sources go into producing electricity or go directly to the end sources. And then we use that for a lot of different uses, right? And you're going to see when you look at emissions breakdowns, you're going to see different breakdowns where you break down into transportation, into heating, or is it for electricity, is it for heating, or is it for industry, and so on. So it's important to have an idea of where these emissions go. But this is, how do I say this? It's difficult to get one single way of breaking down emissions. So you'll hear different numbers, and like if you try to add them up, depending on how it's cut, they don't add up because things that are used for heating then go into industry, so you can double count and so on. Okay, so then just looking at the electricity, and here what I want to flag is you hear a lot about the energy transition, and the first point is decarbonizing electricity. It's really important to understand that we're nowhere near there. So this is emissions from the whole world and the US. And you can see that for both of them, about 60% of electricity comes from coal or from gas. And it's more coal in the rest of the world, and it's more gas in the US. That's because gas is cheaper here. But you can see wind and solar all the way to the right there. They're about 10% today. So we still have a long ways to go if we want to actually get to a net zero future. Okay, and then one other point that's really important for context setting is understanding scope 1, 2, and 3. And this might be preaching to the choir here, but it's really important for you to have an idea when people talk about scope 1, what does that mean? In general, scope 1 is whatever within a company, whatever the company itself is burning. So if you buy gas and you burn it, that's scope 1. Scope 2 is the energy that you buy. So when you buy electricity, when you buy steam, that's scope 2. And then scope 3 is everything else. And what is everything else? It is if you're a manufacturer and you buy from somebody else, the carbon that's embodied in that stuff that you're buying is scope 3. And then when you sell to somebody else and they use your product and that creates emissions, that's also scope 3. And this is really important, especially for some industries. So for example, if you think about a company like Exxon or Shell, they sell stuff that other people burn, right? So that's scope 3. So when Shell says that they have a net zero goal for scope 1 and 2, that doesn't really include the biggest source of emissions, which is their scope 3. Same thing for like GM. GM might say, we're going carbon neutral, but if they say we're going carbon neutral for scope 1 and 2, then you might still be producing ICEs or internal combustion engines, which people are going to use and burn diesel or gasoline to run. Okay, so open up. If you guys have any questions about anything that I say, please ask, and we'll have some time for Q&A at the end as well. Now, going to solutions for decarbonizing. And here, we're going to look at 3 different buckets. The first one is electricity, and I've talked a little bit about this already. The biggest point to understand is that the crux of the energy transition is decarbonize electricity and then electrify everything. Because a lot of the ways that, or almost the only way that we know how to get energy without emissions is through electricity. So the main point to understand is how can we decarbonize electricity, and then how can we use electricity for the other end sources. Mostly. There are some other solutions as well that you can use for that. So there's electricity, then heat and materials, and then transportation. So going into electricity, and this is going to be the focus here, just to have an idea, is everybody here familiar? I'm flagging a few terms here that I think are really important for people to have familiarity with. Is everybody here comfortable with these terms? Or like raise your hand if you're not very. Okay, so I'll go into this a little bit because I think this is really important. So kilowatt hour, megawatt hour, and gigawatt hour, these are units of energy. So this is talking about an actual amount of energy, and you can think about it as like how much energy you get when you burn a liter of gasoline. It's about 10 kilowatt hours. Or when you burn 1,000 cubic feet of natural gas, you get about 1 million BTU. So this is energy. And here, like, what's really important is to understand that this is energy, and the one that's beneath it, kilowatts, megawatts, and gigawatts, that's power, right? So to get from power is energy divided by time, and you multiply by hour, you get kilowatt hours, and so on. So this is just important because people are going to judge you if you misuse this. Then a ton of CO2 is a ton of CO2, and the difference from ton of CO2 to a ton of CO2 with an E in front of it is this is CO2 equivalent. So when you talk about methane, you can convert from methane, like tons of methane, into tons of CO2 with a conversion factor, which will depend if you're looking at 100 years or 20 years, but that's like another can of worms. But it's important to understand the distinction between the two. Then 8760, this is like, a lot of times you're going to hear about, like, this is going to produce X megawatt hours per year, or something like that. And the way that you get from megawatt hours to megawatts average, or you have a solar site that can produce 100 megawatts peak, but then it has a capacity factor, meaning it's producing at 22% of the time, or something like that. So, right, so, sorry. If you have 100 megawatts, and it's producing 22% of the time, so it has a capacity factor of 22%. You multiply 100 megawatts by 22% times 8760, which is the number of hours in a year, to get how much electricity is actually being produced. So it's useful to have these numbers and to have an idea of scale on these things, so that, like, when people talk about, oh, I'm going to install 2 megawatts in my roof, does that actually matter? Right? Because it's important to know so that you can't be duped as easily. Then peaker, baseload, combined cycle, open cycle, that kind of thing. That's talking about types of power plants. So a peaker is something that you run a few hours a year. Baseload is something that you have to run almost the whole year. So for example, a nuclear plant is baseload, so you can't really turn it on and off. Combined cycle is like a gas plant that's more efficient. Open cycle is a gas plant that's less efficient, but they can ramp faster. LCOE is levelized cost of electricity. This is really important to understand. And this is how usually people talk about the price of a technology, is you talk about LCOE. This is going to be basically levelized all the costs to a year, and then you divide that by how much electricity is being produced. Capacity factor, I already mentioned this. This is percentage of the time, like you have a nameplate capacity, you're producing at X% of that. And then dollars per megawatt hour, it's important to have an idea of what's cheap and what's expensive here. This is usually LCOE. And then dollars per watt is like, when you talk about solar, for example, you hear that solar costs something like $1 per watt. That's per watt of installed capacity. And then if you want to get from that to how much electricity is being produced, then you need the capacity factor. So anyway, that was very fast, I know, but these are terms that you probably are going to hear a lot about, and it's helpful to have an idea of what they mean. Okay, so going into solar. And this jacket is warmer than it looks. Going into solar. Solar is probably the biggest source of renewable electricity going forward. It hasn't been in the past, so in the chart that I showed you, there's still much more wind than there is solar. But that's because solar has dropped in price dramatically over the past few years. There's been a bump in the last year or so with the whole COVID thing, but solar has been like getting down in cost like crazy. So this is, again, dollars per watt for residential and for utility scale. You can see residential is more expensive because like there's all the installation cost. And another thing that's important to see for solar, like this is a chart of US solar resource. What this chart, or it does show, but it's harder to see, is that the really bad solar isn't as bad as it seems here. Like really, really bad solar is like half the capacity factor of really good solar. So that's one good thing about solar, is that in general it's very like widely available, right? So even here in New England, you think, wow, this place has no sunlight. It's still like about half as good as in California, which is not the case for wind. So then going into wind, kind of the same thing where costs have been going down. One thing to flag here is that costs have been going down much slower than for solar. Solar started off much, much more expensive and got cheaper slower. And it's important to understand like the factors that led to solar going down as dramatically as it did, especially because like people use solar kind of as a proof that everything will come down in cost dramatically, and that's not necessarily the case. Right, so it hasn't certainly been in certain technologies. So another thing that's important to understand, especially in the US context, is where the good wind is. And here, I really like this map because the white here, it shows there's no wind here. Like there is wind, but effectively you never build a solar plant, wind plant in Georgia because the wind is so bad. Yep.
Do you have any sense of kilowatt-hour variable costs? Is that like an installed levelization of the installed cost, just the y-axis thing?
Yes. So yes, that's a good question. So this here is showing cents per kilowatt hour, and the other one was showing dollars per watt, and that goes back to like what I was talking about. The way that you get from one to the other, this is when you get from dollar per watt, where you install, for example, let's say that you want a 1 megawatt solar plant. A 1 megawatt is a million watts, so you would pay $1 million up front for a 1 megawatt plant. Now, this 1 megawatt plant is going to produce maybe 20% of the time on average, so a 20% capacity factor. So how much electricity it's actually going to produce is going to be 8,760 times 0.2 times 1, right? So that's going to be about 1,600. And then what you do is you levelize this cost. It's going to cost about $1 million. So you levelize the cost. It's going to be like probably about 100,000 per year. And then you divide one by the other. You get to like an actual cost, cost per megawatt hour. And then cost per kilowatt hour is 1,000th of that, right? So like this is equivalent to like 10 cents per kilowatt hour. Is the same as $10 per megawatt hour. Sorry, 100. Okay.
Yeah, you talk about solar and dollar per watt because you can put it in multiple places. In Boston versus California makes a big difference. For wind, you only put it where it's cheapest. So dollar per kilowatt hour makes more sense.
Yeah, you definitely don't put it like, because for wind, I'm not going to talk about this, but wind is proportional to the wind cubed. So the difference between a place that's a little windy and a place that's more windy is very big. So that's why like it's white here. So the US has 3 regions where you can do wind, basically. There's the wind belt here. That's the greatest wind ever. Really, really good. Really, really cheap electricity, but there's basically nobody there. So then it raises a problem with like getting this energy from here to where a lot of the demand is in the US is close to the coast. So there's a huge problem with that. In Texas, like this is probably a great example because they build a lot of transmission to get this really good wind from the panhandle here. And as a result, about a third of all the wind in the US is in Texas. The other 2 regions are by the coasts. And the difference here is the East Coast has really shallow waters, so you can do offshore wind more easily. So there's most of the offshore wind developed in the US is there. And then in the West Coast, there's also pretty good wind, but then you have to go to deeper waters. So then you need floating wind. And basically the difference is onshore wind is great and it's really cheap. Offshore wind is really expensive, and floating offshore wind is insanely expensive. So like there's, it's hard to make the economics work, and that's why a lot of the offshore wind is being driven by policy. Okay, so you're gonna hear probably 100,000 times that the wind doesn't always blow and the sun doesn't always shine. Seriously, like it bothers me. And there's a lot of ways to deal with that, right? So here I'm mentioning a few. Load shifting or demand response is basically you pay somebody to not use electricity when you don't have electricity. So for example, if you're in California, if you charge your car during the day, there's a lot of solar there, versus during the night, there's not. So that's one of the ways, and that's probably the cheapest way that you can deal with intermittency. But it's hard because then you need people or companies to change their behavior, right? So you have to really incentivize them to do that. Then there's storage, obvious, right? Like you have a battery or you have a pumped hydro plant, you store electricity for when you need it. And I'll talk a little bit about that. There's transmission, which is great and impossible to build. Seriously, like really, really hard. Because in general, people don't want it near them. And like even in very rural areas, there's a lot of resistance to that. So you're going to hear a lot about this as well. NIMBY, not in my backyard. Then you can have dispatchable or firm resources, and this can be a lot of things. One, it can be just keeping some of that gas for running 5% of the time when you don't have electricity. It could be having nuclear or geothermal, and I'll talk a little bit about that. Or in the limit, it could also be making hydrogen and then burning it, but that's currently really, really expensive. And then the last one is just overbuilding the renewables, right? And this is an option that, like a lot of people talk about renewable energy being curtailed as if it's like necessarily a bad thing, but it can be a normal thing, right? Because if you have a grid that's fully decarbonized, it might be better for you to build a little bit more solar and just curtail it at some times, and then you have enough for when you need it. Right, so going a little bit into storage, storage is very important and it's being deployed a lot right now. And there's 3 technologies that are widely deployed. The first one that's most of the deployment today is happening is with lithium ion. And this is mostly LFP, or lithium iron phosphate, which, important to understand, has no cobalt. When you hear about the whole cobalt thing, that's with another lithium ion chemistry that's usually used for cars. So I'll talk a little bit about materials later. Then there's pumped hydro, which is interesting because most of the pumped hydro that we have was built in the 70s and the 80s, actually to accommodate nuclear. In the grid, and pumped hydro simply works, you have a reservoir in the bottom, you have a reservoir up a mountain, and when you have excess electricity, you pump water. When you have a need for electricity, you let it go down and spin a turbine. And then there's compressed and liquid air, which are smaller right now, but are promising technologies, and there are some pretty big batteries that are built with this. And basically what you do is, like, it's kind of obvious. You compress air, and then you let it run through a turbine. When you need electricity, and liquid air is pretty similar, but you cool it down enough so that it's liquid, and then you need a lot less storage versus compressed air for the same amount of electricity. And then there's evolving tech, and here I'm just mentioning two technologies, which is zinc bromine and iron air. Both of these actually got grants from the DOE to get demonstration plants up and running. So we'll see how that goes, and that's really exciting. And then the other thing that you hear a lot about is long duration energy storage and the hours of storage. And what's really, really important to understand here is, in general, what you want now is shorter duration, because a lot of the times, like, you don't have moments right now where you have 10 hours that there's too much electricity and then 10 hours that you have too little electricity. Usually it's 2 hours during the middle of the day in California, or a few hours in Iowa that you have too much wind, and then a few hours that you have a shortage. So right now we really need short duration storage. But for the future, when you say, okay, how do we get to net zero, to 100% decarbonization, then you need a lot more storage, so a lot more hours. And that's when these technologies really become important. Yep.
Yeah. What are some of the companies developing this evolving technology, batteries like iron air and zinc?
Yeah, so iron air, the like next door here in Boston, there's Form Energy. They're doing like a $100 battery, which is really exciting. And then there's also Embry that's close by. But there's like probably hundreds of startups that are doing either like for the grid or for grid scale. There's a lot of people working on this stuff. And then even like when you talk about solid state lithium ion batteries, there's like stuff that you can put in your cell phone. So there are companies that are working on that. So there's a lot going on. Cool. Then there's firm carbon-free generation. And here there's basically nuclear, geothermal, and hydro. Nuclear is great, and we should definitely keep the nuclear that we have going. But building new nuclear is crazy expensive. So there's people developing new technologies that they say could become cheaper. And that's like to be seen if that's going to work or not. The challenge here is also that it takes a very long time. There's a huge amount of regulation around nuclear. So even if this tech works wonderfully, it will probably be another 10 years before we actually see one of these. But there are some really cool companies working on this stuff. Then geothermal, there's basically the core of the earth is really hot. So if you dig a hole deep enough, you're going to find hot stuff that you can use to produce electricity. And most of the geothermal, or all of the geothermal that we have right now, is really shallow geothermal, where you have like a geyser or something like that that has steam close to the surface. So then you can get that steam and produce electricity. So for example, Iceland has a lot of geothermal. The US is actually the country with the most geothermal, but has something like a gigawatt. So really not a lot, like 0.2% of electricity is from geothermal. But then there are some companies working on advanced geothermal, which is like digging really, really deep so that you can get to basically geothermal anywhere in theory. Also kind of unproven-ish yet, especially the economics. So to be seen if that works, but it would be great if it did. And then finally there's hydro, right? Which is great. And again, we have a lot of hydro already. That's a very traditional way of producing electricity. The problem is a lot of the hydro resources are already being used. So it's not like you can build a lot of new hydro. To some extent, you can build more pumped hydro, which is again a form of storage. And then there's also run-of river that's relatively new. So instead of building a huge dam that floods a big area and you have to displace people, you just let the river run and do a bypass. But again, most of the resources already tapped into. Okay, so now, like this is a lot. Oh man, NREL, I was going to say DOE. NREL, which is the National Renewable Energy Laboratory, ran a bunch of studies looking at how to get to 100% decarbonization for electricity. And this is, like each line here is a scenario where they're saying, okay, if nuclear doesn't work out, or if geothermal does work out, or if the cost of batteries or hydrogen gets a lot lower, right? So each one of these is a scenario. The ones in the bottom here are basically the no policy scenarios where policy doesn't really help. And we're already not here because of the IRA. And what's really interesting is that here solar is yellow, storage is pink, and wind is blue. You can see that in basically all of these scenarios, we have a lot of solar, wind, and batteries, right? So what's really important, and this line here is the current installed capacity in the US. So you can see in basically all of these scenarios, there's a lot more wind, solar, and batteries. And this is important because you're, again, going to hear a lot about technology. And it's important to set the context where having new technology is really important. So it'd be great if we get cheap nuclear. But it's very unlikely that we won't need a lot of solar, wind, and batteries. So we should definitely start building now. So that's the main message that I want to convey here is we definitely need to be building faster. Okay, and then just to mention this so that you know that this exists, when people talk about DER, that's distributed energy resources. And this is as opposed to the traditional grid, quote unquote, which is you have generation, then you have transmission, then you have distribution, and then you get to customers. That is the way that the traditional grid works. And with DER, you enable the customers to also produce electricity or to also have energy resources. So that can be a battery or something like that, which integrates to the grid as a whole. Well, 2 points here. One, people talk a lot about this with the advantage of giving power to the people and enabling them to have ownership on this. There's also arguments to be made on resiliency and so on, and then fairness. But one challenge is that in general, things that are on the customer side are more expensive, right? So just because of economies of scale, if you put 5 solar panels, it's more expensive than putting 50,000 on a field. So that's a challenge that needs to be overcome. And the other thing is finance, because then financing a small installation is generally very hard because like how do you get assurance that the person is going to pay you? So a lot of what's being deployed right now is with richer people who have the money to install this themselves. Okay, then the last point that I'll mention is on energy efficiency. And here, sorry, I'll have a few rants. One huge success is light bulbs, right? So if you look at the incandescent light bulb, then fluorescent light bulb, then LED. LED is like on a lifetime basis cheaper, right? It's more expensive when you buy it, but it's much more efficient. The sad part is that we're not fully transitioned yet. So it annoys me a little bit. A lot of the lights at MIT are fluorescent light bulbs. And that's like, it goes to show that it's hard, right? It's hard to get people to change. And even when it's like an institution that has a lot of money and goes to decarbonize, it's still not something that's automatic, right? And then there's also things like revolving doors. I'm excited that they're back to work here, like they weren't last year. And double pane windows and heat pumps, things like that. That can all increase efficiency of houses, and it's really, really important to move to these solutions. And then the last point that I'll mention on energy efficiency is like the behavioral side of like getting people to change. That's really, really hard. So like getting people to turn off their AC or to buy, like if you're going to buy a vehicle, it's much better if you can drive a smaller car. Like when I got to the US, I was shocked at the size of cars that people drive here. But one thing that I was also shocked is that a lot of this is actually driven by policy and by regulation. So, for example, you can get, if you have a pickup, you can get some tax deductions that you can't with a normal car. So that's one way that the government is actually nudging you towards buying a pickup instead of buying a normal car, because then you can get more tax deductions, right? And then there's a lot of things like that where you make fuel standards, but then the fuel standards are relaxed if it's a bigger car. So these are things that, like there's one component that is customer preference and like what people actually want. That's really hard to change. But then the other thing is, what's the regulation trying to get you to do? Right? Okay, so moving on to heat and materials. So here, heat is a huge part of emissions. And what's important to see is that there are different temperatures that you need. Here it's broken down between less than 100 C, which is boiling water, and then 500 C, which is maybe 1,000 degrees Fahrenheit, sorry. And you can see that for industries, you need a wide range of temperatures. And there are different solutions that work for each of these temperatures. So here I'm breaking down by big numbers. So heating for very low temperatures where you need for like heating a house or something like that. Then high temperatures, which is a lot of industrial processes, and then very high temperatures. In general, for low temperatures, you should 100% be using heat pumps. And here I'm mentioning this on purpose. COP is coefficient of performance, which is a measure of efficiency. It's basically how much heat you get out versus divided by how much energy you put in. And because of the magic of thermodynamics, you can actually get more heat because you're taking heat out of the environment. With heat pumps, you can get more heat than you put in as electricity, which is great. But that doesn't work out for very high temperatures. So that part, that doesn't work. Then there's resistive heating that has a COP of 1, right? You're just running electricity through a wire. You should probably not do that for low temperatures heating, but for high temperature, it's kind of what you can get. Then there's hydrogen, and a lot of people say that hydrogen is really good for industrial processes because it can get to very high temperatures, which is difficult to get with other technologies like resistive heating. Then this is probably my favorite one, which is you have, oh, yeah.
Yeah, what's the difference between blue and green?
Yeah, so good question. So blue hydrogen is you have gas, you burn, you do steam reforming on the gas, and then, which is the traditional way of making hydrogen is you react methane with water, and then you produce hydrogen and CO2. And then with blue hydrogen, that's gray hydrogen. The difference between gray and blue hydrogen is that you capture the CO2 after, and then you do something with it. Hopefully you put it underground and never see it again. And then green hydrogen is you use electricity to produce hydrogen, which is then the requirement here is for it to be green is that you need to run it on renewable electricity. Because if you burn gas to produce electricity to then run an electrolyzer, you're going to be much worse off than if you just produce hydrogen directly from the natural gas. So it's really important that it's renewable electricity. And then there's a whole discussion here. I won't get into that with the whole annual and hourly matching thing, but you can look into that. The DOE is still deciding the requirements for what exactly is green hydrogen. Okay, then resistive heating and thermal storage basically means you heat up material. So like you have a bunch of bricks or something like that, or sand or water, and then you store the heat for when you need it. And the good thing is that it really pairs well with renewables, right? So if you have a lot of solar, you heat up something, and then that's a form of storage to balance the grid. And then the last one is nuclear and geothermal. And the really good thing is if you do nuclear or geothermal to get to heat, it's much more efficient because you don't need to do the thermal conversion from heat to electricity. So then you go for nuclear from like 30% efficient to 100%, right? Because you're actually using that heat. Okay. And then there's materials, which is a huge part. These 4 materials here that I'm showing are 20% of global emissions. Cement is the biggest one. And cement is tough because the reaction that produces cement itself produces CO2, right? So basically it is you have a carbonate that is a molecule that has a CO2 in there. You need to heat it up to produce an oxide, so calcium oxide, which is the main component of cement. And then that releases CO2. So the CO2 is inherent to the process of how we produce cement today. And there are some companies that are looking into maybe not using a carbonate, or you can do the same process but then capture the CO2, or you can mix the CO2 back into the carbonate, into the oxide, and capture some of that CO2 into the material. Then there's steel. There's Boston Metal, also like very close to here, which is really, really cool. They're trying to do direct electrolysis of the iron oxide. So you heat it up, and then you run electricity through it to produce steel versus the normal process, which uses coal. And then there's aluminum ammonia. And what I'll mention on, well, aluminum, you need a lot of electricity. So that's the main point. You need green electricity. And for ammonia, you need hydrogen. And the hydrogen, again, is produced from natural gas. So if you have green hydrogen, then you can swap it in here and produce green ammonia, which is easier said than done. Like if you look at just ammonia, if we used all the renewable electricity that we have today, all the wind and solar, to produce green hydrogen, that would still not be enough to supply all the ammonia that we use. We use a lot of ammonia, and that's basically for fertilizers, mostly where it's going to. Okay, so then we get to the final point, that is transportation, right? And transportation is about a quarter of total emissions. This is what I was saying about the different breakdowns that you see. This is a breakdown between heat and power, then industry, and then transportation. And for transportation, about 40% goes into cars, and a third goes into trucks. And then there's about 10% that goes into planes and ships. And few things to realize here. One, planes and ships, we have no idea how to decarbonize. That's their reality. Like, there's no economic way today to run this. You would need huge subsidies to make this work. And the challenge is, like, usually you need very big distances, so you need a lot of energy, and then it's really, really hard to get that much energy from renewables. So what you could do is maybe like do hydrogen and then do CCS and then produce a synthetic fuel that replaces the normal fuels, but that's really expensive. So that one is like very, very hard to figure out. Maybe you can do nuclear ships, so that's exciting, but we'll see. For cars, though, we definitely have a solution. That's pretty obvious. EVs. Some people are still trying to do hydrogen cars, which is a crazy thing. Like, I do not understand why. Because, I mean, yeah, like from a cost basis, EVs are just better. For trucks, sorry about the rant. For trucks, that one is really hard still. You can do a truck EV. The challenge is that in general, batteries are really heavy, and the further you need to go, the heavier they become. And for trucks, the weight is really, really important, because how much weight you have determines like how much you can carry, how much money you can make. So just going over quickly to EVs, two things important. Europe, a few countries in Europe are really adopting EVs very fast. China is surprisingly adopting EVs like crazy. If you look at China, they have about 22% of cars there being sold are EVs. And in the EU, it's even less, like if you look at the EU as a whole. As in the US, it's like 7%. And a lot of it is because of range anxiety. Like in the US, people really like to travel on the highway system and so on. And there isn't a lot of charging infrastructure. So that's probably, and the IRA has a lot of money that's going into that, so that's exciting. But maybe we'll start to see more and more EVs being adopted here. Nice. Okay. Then going to my others category, right? So the first one is CDR. So here I'm just throwing a bunch of acronyms, and it's important to just at least know what these technologies are. When people talk about CDR, that's carbon dioxide removal, which is taking carbon out of the air. Here there are a lot of technologies that can do that. First one is BECCS, bioenergy carbon capture and storage, which is you burn like some kind of plant, and then you capture the CO2 and you put it underground. Then there's DAC, direct air capture, which is like getting CO2 directly from the air and then doing something with it, which is really, really expensive today and needs a lot of energy. So there is a lot of research that needs to be done to get that down. Enhanced rock weathering, I really like this one. It's like you dig up some rock that's alkaline. So think about like the opposite of making cement. You dig up an oxide, you expose it to the air. With water, it reacts with CO2, and then it makes a rock that's stable. And this process happens naturally. You're just making it faster. Then there's afforestation or regenerative agriculture, which is like trying to put it in organic matter. Then there's problems with like the CO2 actually staying there, but that's the idea. Then there's CCUS, which is carbon capture, utilization, and storage. That is, you have a point source, like a coal plant, you capture the CO2, and then the U means using it, which is usually not great, because if you use it, then like you're basically making something that will end up in the atmosphere in the end, probably. But then the S means sequestering it, so putting it underground so that it hopefully doesn't get out. And then there's carbon markets, which is a very, very, very big topic. There's basically two kinds of carbon markets. There's voluntary carbon markets where like Microsoft wants to decarbonize, they're not forced to, but they can go into the market and buy an offset that can have different qualities, and there's a whole can of worms there. And then there's compliance markets. So for example, in the EU, if you want to emit a ton of CO2, you have to hold a permit to emit that ton of CO2, so you have to buy that, at least for power plants. So these are two different kinds of carbon markets. And in general, the voluntary carbon markets are a lot smaller and have a lot lower prices on average than the compliance markets. And this is, like, I feel a little bad for all the economists that keep repeating this, that we should really do either compliance carbon markets or a carbon tax to decarbonize, because that's the most efficient way. And like, it's really, really hard to get politicians behind that because people don't like paying more for anything, right? So it's hard. A lot of the incentives that are being put forth today are in replacement for a carbon market, but it's really hard to get that to be efficient. And if you want to learn more, last year's Sustainability Summit was on that, so you can go there, see that. Okay. Then there's non-CO2 gases. Three things that I'll say here. First, methane is really, really, really important, and we talk about it way too much, way too little, sorry. It's about a third of global warming today, and the good thing about methane is that if you stop emitting it, it reacts with the oxygen in the atmosphere and produces CO2, so it goes away in about 20 years. So it would be great if we did that. But it also has a lot of sources. And here, like, the three big ones are fossil fuels. What's the name of this? Like a dumpster? Landfill, thank you. So there's landfills. Basically, when you have a lot of organic matter reacting without oxygen, it produces methane. And then a lot of places you burn that, so you collect that and you burn it, which is much better because then you break it down into CO2, which is a lot less warming. And then the third one is agriculture. And this is mostly cows, but also rice is a big source. But yeah, cows are huge. I think if you look at, like if cows were a country, they would be the third biggest after the US and China. So. And then there's other gases as well, F gases, I mentioned nitrous oxides, and then there's SO2, which has a cooling effect, but it's toxic, so not great. Thankfully, we're getting away from this. This is mostly coming from coal and high sulfur petroleum, which like some ships burn. But there's fuel standards to get that out. Okay, and then there's materials, which is, again, a whole other can of worms. There's a ton of materials that are really important for the energy transition. I'm mentioning a few here that you'll probably hear more about. Copper is used for everything like that has wires in it, basically. Lithium, cobalt, and nickel are materials for batteries, and cobalt is really bad because it comes from the Congo and like a lot of human rights violations there, and it's like basically only in the Congo that you have cobalt, so that's kind of terrible. Yeah, so all these three are really important. I mentioned lithium iron phosphate. You can do EVs with that, and mostly in China they do, but they have a smaller range. So that's why a lot of the batteries that are built for EVs in the US are with these three materials. And then there's aluminum, which is used for like everything from EVs to planes. Okay, then I put up a few resources here. I really recommend these podcasts. They're great. One thing that I'll say on these is that everybody has an opinion on this stuff. You saw that I have some as well. So it's really important for you to see like where people are coming from and understand if what they're saying makes sense or not. And for that, I think it's really important to hear a lot of people talking about these things. Then there's a couple of books here. There's a few channels on YouTube that I really like. And there's a bunch of classes at MIT. So I took these two that I really, really recommend. They're amazing. And then there's also some over SIP or LEAD that I hear are great. So we're going to send this over to you so you can see it. Okay, so that's what I had. I'll open up for questions.
Thanks so much. That was very helpful. I'm just wondering if you could talk a little bit more about storage. I'm not like I don't understand how much of the energy that you create just do you lose based on like when you store it? How does that change over time? Mm-hmm. And are we getting better?
Yeah, that's a great question. So that's going to depend a lot on the technology. So usually with lithium ion, you get something like 85% of the energy that you put in, you get out. The problem is that lithium ion is very expensive, so you would only put it in a place where you expect it to charge and discharge every day, right? So that's why usually you do a 4-hour battery with lithium, because then you spend 4 hours charging, 4 hours discharging in the day. If you had, for example, you can do a 20-hour battery with lithium, but it's going to be 5 times as expensive, and you're probably going to make less than 5 times more money. And then there are some technologies that are much less efficient. So for example, if you make hydrogen, you lose about 30% just on making hydrogen. Then you usually have to compress it, and that's another 10% or so. And then you burn it, so then you probably lose another 20%. So, you lose another, usually like 30-40%. So then you probably get to 40% efficiency if you're lucky. But that may or may not matter, right? And this is going to be a function of how cheap are the renewables that you're using, and then how cheap is the stuff that you're building, right? Because if you had a battery that's 30% efficient, but it's dirt cheap, that doesn't really matter, right? Because then you can only buy electricity when it's negative and then only sell when it's super high, and that's okay. But in general, you want efficiency to be higher. So yeah, that's definitely a consideration as well.
Real quick, the CTVC screenshot that was on there, they have a whole like long newsletter about different storage technologies. That's worth checking out.
Thanks.
In terms of the clean electricity transition, I'm just curious to hear what you think are the biggest barriers and bottlenecks. Obviously, there's policy. I heard some things about land use.
Yeah.
Yeah, curious to hear more and what are the conversations going on?
Yeah. I would say in the US, it's probably the interconnection process. So basically how it works is if you want to interconnect a new resource, and this is for grid scale stuff. So if you have a 200 megawatt solar plant that you want to interconnect, and you put up a request for that, in a lot of the US, that's going to take 4, 5, 6 years to get the right to interconnect, and you're going to have to pay a lot of money for that. Then there's like building transmission is really hard, and a lot of times you need to build transmission so that you can build more storage. So I would say for the US, that's probably the biggest challenge. For the rest of the world, it's probably financing for poorer countries, because it's really hard. Like a lot of these projects, and I'm seeing this in Xterra, like the US increased the interest rate. And it's interesting because that basically, like all the subsidies that the IRA is giving, they're almost wiped out by the higher interest rate. Because you need, like I mentioned this, for a 1 megawatt solar plant, you need about $1 million. So you need a lot of upfront capital. And if the interest rate is high, then you need to pay a lot more in interest, right? So the economics becomes a lot more challenging. And I'm from Brazil, and the base interest rate there is something like 10%. So you start from that. So getting these projects to be economical is a lot more difficult if you're in a higher interest rate country.
This might be more of a science question, right? My question is more around like the embodied thing. So like when we say we're looking at solar energy. So if the solar panels are manufactured in like with like more grid intensive electricity, and then like it might not be as efficient as we would expect it to be. So do you know if there's like research going on in that way, and like are people looking into like the embodied versus like use, like basically what they're getting out of it?
Yeah, that's a great question, and that's something that you hear a lot about, like when usually coming from people who don't like these things, and it's important to know the numbers, right? So the numbers that I've seen for solar panels is that you need about 5 to 10% of the energy that they produce to produce them. So even if you start in a grid that's very dirty, like you're starting usually in China, where there's a lot of coal, it's still a lot better than if you just continue burning natural gas. So that's for solar panels. For wind, you often hear that the blades are not recyclable, and they're not, like, and that kind of sucks. Like some people are working on doing things with them. One thing that you can definitely do is throw them in a cement kiln and burn them, but that's not great. So that's tough, but it's also like important to have a sense of scale, right? It's not like most of our waste is wind blades, or solar panels. And then the other thing that you often hear is for EVs, there's a lot of embodied carbon that goes into making an EV, and the answer is kind of the same. And then there's also the energy that goes into charging the EV, where if you're in a very grid intensive, like carbon intensive grid, that can be worse. Usually in the US, it's not. Like it would only be if you're in a state that has a lot of coal. So the maps that I've seen are like only a tiny part of the US. It's actually worse to drive an EV than a normal ICE car.
You were speaking a bit to alternative greenhouse gas emissions, but I feel like really so much focus is on CO2, even though you were talking about methane, and I know I worked in agriculture before. Nitrous oxide is actually warms the Earth 300 times more than CO2. Why do you feel there isn't so much focus there, and are there mechanisms and markets incentivizing reduction in those areas as well?
That's a great question, and I think the same thing is true for agriculture. I think it's underappreciated how much of emissions comes from agriculture, and how much of the solution can be there as well. There's one thing that is, like, it's probably easier to talk about. It's like more obvious and tangible, right? Because like when you're burning something, it's clear that you're emitting CO2. With methane, you start to get into these discussions. Should we be looking at 20 years or 100 years or not, right? Like, what kind of time window should I look at? If you look at 1,000 years, like, it doesn't matter, right? Methane breaks down into the atmosphere and it doesn't matter. So yeah, there's that. But then there's some exciting news. So for example, I think it was with the IRA, they actually have a fee on leaked methane. I don't know the details on how exactly that's being implemented, but hopefully they will start to move things, because like in the US at least, and Shiv can talk more about that, but most of the emissions from methane come from natural gas. So if you curb the leaks, then that reduces that. But it's tough. Like, I definitely think we should be talking more about this stuff.
Can I do a quick question on the economics of renewables, especially solar, which is quite cyclical during the day? So I know you have like a battery or an energy storage solution, but that's still too expensive. I'm coming from Chile, and the problem there is that during the day, the price of the energy in the grid goes down very much. So they have like subsidized to solar, putting a stabilized price, but that's not like a long-term solution. What's your thought on it?
Yeah, that's a hard one, and especially in a deregulated market, where, like, with the deregulated market, when there's a lot of supply, the prices come down, even if the value of that energy is high, it doesn't matter, right? Because you're setting the price at the marginal cost. And in the limit, if you only have renewables, then the price is set to zero. So that's tough. I honestly don't know the solution for that. It would probably be like a mixture of regulation and like market reforms. But yeah, that's a big question for academia, honestly, that I've seen.
Something California is doing, or has done, I think has kind of worked, is shift demand via time of use pricing. So it's like, if I am charged more for electricity at 6 p.m., then I'm likely to change my behavior, and therefore a solar farm developer would make more money because I'm shifting my demand there. Like that's only a portion of the solution.
Do you get too much pushback from the people?
For time of use pricing?
Yeah.
I mean, like, what are people gonna do? I don't know.
Yeah, the other thing is, like, people don't usually change their behavior, because like you don't really have, like, especially in California, like that's super complicated. Like if you look at like some of the tariffs that they have, is like, oh, you have 5 different types of tariffs, and it depends on the season and things like that. And like nobody, like even like us energy nerds, like can't really wrap our heads around that. So it's tough to get people to change, but then technology can help. So I just want to be mindful of time. If you guys want to continue here, like, continue talking.
We'll take one more question, and then we'll have to wrap it.
Yes. Okay, so thank you.